I was asked to talk about galaxy photometry. So let me start with a big disclaimer, which is that this is not going to be a complete review of galaxy photometry by any means. I'm really going to concentrate on the things we've done in the context of our own kilo-degree survey, KiDS plus Viking, which I'll tell you about in a second. And much of what I'll describe is in these two papers here, for the references you can see on screen. So what I'll try to do in the half hour that I have is a kind of statement of the problem of galaxy photometry. What is it we're actually trying to measure, and then possible approaches that have been taken, be kind of abstract, and then I'll dive into how we're actually in practice doing things for kids, and end with some things about how we might improve things further. I'm not going to talk about overlapping sources at all. That's so deblending is a whole separate issue. Our deblending happens in our recleansing pipeline, which is not what I'm going to be talking about today. In practice, basically, we throw away sources which are affected by blends rather than trying to measure them. And I'll say a little bit, but not much, also on our photometric calibration. So one slide on KiDS and Viking. So KiDS, it's a 1,300 or so square degree survey in two big patches of the sky. There, for those of you who've been around long enough, it's the two areas of the 2DF redshift survey, basically. And we're covering these areas in a total of 9 bands from U to K using 2 different instruments. The U, G, R, and I bands are done on the VST, the VLT survey telescope, Arnal. And the 5 near-infrared bands from Z to K are done on Vista, which is a 4-meter on a hill right next to Arnal. These are different instruments, different cameras, different pixel scales, etc. And so part of what I'll talk about today is how we deal with the problem of trying to combine all those data in a way that basically is blind to the, in the end, ends up being blind to the instrument signatures themselves. All right. So what do we mean by galaxy photometry? And this is actually a question that different people will answer differently. And basically you can focus on 2 things. You can say, I want to know the total flux of every source of every galaxy. So you might want an SED of the total light emitted in various bands of a galaxy to turn it into stellar luminosity, stellar masses, do things about the stellar mass budget, etc. Or you can be interested primarily in colors, and those are really 2 different questions. So colors you might want for studies of the stellar population, or about photometric redshifts or star formation rates, things like this. And depending on which of these 2 you want, and you need to think carefully which of the 2 you want, you actually end up setting yourself different requirements. And these requirements will only coincide when you're looking at unresolved sources, where of course total magnitude is the only flux you can get. So I'm not talking specifically about surface brightness photometry here, but I am talking about photometry of extended sources. So let's start with a really simple example to illustrate what I'm trying to do. Fundamental problem, of course, is galaxies have no sharp edges, and so they will always have a wing that disappears into the noise, and you only have very limited information about that wing. And so in practice, one way or another, explicitly or implicitly, you end up modeling what happens as your wing disappears into the noise. And as soon as you're modeling, you have to deal with model bias, the effect that your model may not be a perfect description of your system, of your source. So here, for example, let's take this red profile. This is a simple 1D example of an exponential galaxy with a total flux of 1, scale length A. And let's say we try to model this galaxy with another exponential, but with the wrong scale length. And so then the question is which, so here's the truth, flux of 1 galaxy. And here's our model, a galaxy with a scale length of B and flux 1. And so we try to fit the amplitude of this model in a kind of least square sense, or whatever you like, that gives you the best fit. And from that you read off F, and that's your estimate for the flux. Now, if we assume that the noise is uniform everywhere, background limited, that's perfectly reasonable. You can just figure out what the least squares fit would give, and it gives you this expression here, 2b over a plus b. And the important thing about this expression, and this is very simple in this simple analytic case, but it's a generic result, is that this expression is not equal to 1 if your model doesn't have the right scale length. Right? If your model is too long, then you end up imagining more flux in the wings than is really there, if you like. So F is overestimated. If your model is too compact, if the scale length is smaller than the scale length of the system, you end up underestimating the flux. And unless you have good enough data to figure out which, to estimate the scale length separately, you're going to be stuck with this uncertainty due to the model, the model bias. And this really is extremely generic. Here's the same model, but now using Gaussian galaxies, and you get similar result. Now you end up estimating a flux, which looks like this. Again, it's not equal to 1 unless A equals B, unless your model and your galaxy have the same scale. Now the Gaussian model is useful because it allows me to make another point, which is that in practice, we observe things with a finite PSF. There's resolution, so you end up blurring your data. So what you have to do to compensate is blur your model as well before you fit it. That means that in the Gaussian, you just add the size of the PSF P in quadrature to both your data A and your model size B. So then this expression here turns into this one here, which has the size of the PSF in it. And you see the bias is still there, but it's actually different. For different values of P, your bias will be different. So your model bias A is always there, unless your model is perfect. And it's a function of your data quality of your point spread function. Right? The same galaxy fitted with the same wrong model is going to give you a different flux under different seeing conditions. So basically this means that truly total magnitude measurements are hard, if not impossible. They're model dependent, they're observation dependent. And so I would say that to some extent, depending on the quality of the data and the source you're looking at, they're actually an ill-defined quantity. And I haven't even talked about chi-subtraction, which is yet another aspect of this whole business. And so, of course, we do want magnitudes for galaxies. We do want flux measurements. And so there's a wide variety of proxies that are in use to give some characteristic measurement of the flux of a source. And we're used to many of these, the Petrosian magnitudes from Sloan, the aperture magnitudes with various kind of correction schemes, isophotal magnitudes where you try to extrapolate what happens outside the isophotes. You can get your isophotes by fitting a model or by using segmentation maps. You can directly fit PSF convolved models, and there's various models you can use that are popular. The point is, all of these are in some sense affected by this uncertainty that I described before, and they all involve treating the points function properly, and both for the measurement and also for the interpretation. Many of these issues were dealt with nicely in Fred Molenkamp's talk on Tuesday. And also, while I'm here, I'd like to give a shout out to people who like to use segmentation maps. There's this very nice code from Robotham et al. Called Profound and Profit, which is a much more sophisticated way than S-extractor of turning an image into segmentation maps. All right, so that's all I'm going to say about total magnitudes. It's something that often you may think you want, but you actually don't want. And often you may think you've measured them, but actually they're very hard to measure accurately. So I'm going to switch now and focus on the problem which usually is the one we do want to solve, which is measuring colors of sources. And of course, ideally, a color measurement is simply the flux ratio of two total magnitudes or two total fluxes. But as I explained before, that's hard. But you don't actually need to go through the total measurements to get good colors. Because why do we need colors of galaxies? It's basically to tell us about the nature of the stellar population, to get the SED of a part of the galaxy, to say something about dust maybe, or to get phase shifts. And that typically means that you can get away with concentrating on the part of the galaxy that is sticking out above the noise. Only use the bright part of the source and make yourself insensitive to the details of the tails at large rate. So you can do this in a proper way that avoids any of the extrapolation errors that model magnitudes are plagued with. And it also allows you to stay in the higher signal to noise part of the source and get more accurate measurements. So philosophically, this means that we're trying to use some sort of aperture to measure the high fidelity colors from the central parts of galaxies. And you can only do this properly if you really carefully account for PSF differences. So here's again one of these toy examples. This is a galaxy with no color gradients. So the dotted lines are the intrinsic profiles. They're the same profile in blue and in green, but it's a blue galaxy, so there's more flux in the blue than in the green. But in this case, the seeing is worse in the blue than in the green filter, and so the blue image is actually more smeared out than the green image. So if you were to do the simplest naive thing of just plonking down an aperture, a top hat aperture on this galaxy, you would get basically completely the wrong answer. You would lose a very different fraction of the flux in the poor seeing blue image than in the good seeing green image. And unless you're able to account for this, you would end up with some sort of color measurement, which is to some extent meaningless, up to the effects of these PSF blurrings, which you haven't taken into account. So you need to do better. You need to allow for these seeing differences. And the reason is, of course, that the PSF scatters photons, and it scatters them asymmetrically because you have luminosity gradients in a source. So this dotted line here, for example, will see more photons scatter out across it than in across it, because there are more photons here to be scattered out than there are photons here to be scattered in. So, and again, the scattering fraction depends on the galaxy surface brightness profile and on the PSF and on where you put this aperture. So mathematically, what you actually measure when you do aperture photometry is this integral here. The aperture flux is just the integral over your observed image, your observed surface brightness profile, O, multiply some aperture function, and then integrated principal over the whole sky, because the aperture function is going to be 0 at large radii. You can replace this observed profile by the intrinsic profile convolved by the point spread function. And so this is what you actually measure when you do any kind of aperture flux measurement. So O is the observed image, I is the intrinsic image, P is the PSF. And A is this aperture function, which in the example I just showed you was a top hat, but it can be, in principle, it can be anything you like. Now with an integral like this, there's a nice trick you can play, which is to swap the multiplication and the convolution. It's a nice triple product. And so you can write this aperture flux as an integral over the intrinsic image, so pre-seeing, multiplied by some weight function. And this is a new aperture function. And this aperture function is just the one that you put on your post-seeing image convolved with the PSF. So I've simply swapped the convolution and the multiplication here. That's a legit thing to do. Now we've turned our aperture photometry into an aperture photometry on the intrinsic image itself. And now this is nice, because now we're dealing directly with the truth, the intrinsic image of your source. And the aperture is the convolution of your observed aperture function times with the point spread function. And so if you have different images of the same source, either through different bands or different times, or that you want to combine, as long as this combination, the aperture you're measuring your observed image with, convolved with the point spread function of that image, as long as that combination is the same, you're always going to be measuring effectively the same part of the galaxy. You're always going to be using effectively the same aperture on the intrinsic pre-seeing sky. And so that's the key to everything we're doing. And so there's various approaches that you can take to make sure that this is true, so that you're measuring consistent aperture fluxes. If you're just comparing two images, if you want to just measure a single color, what you can do is you can convolve each observed image with the other one's point spread function. And then this P becomes the convolution of both point spread functions. And so it's the same for both images. And then you simply use a matched aperture on those convolved images, and you will measure a real color. You can degrade the seeing of the best image to the worst image, again, to make these things match. And people have been doing this for years, and you can do this to various degrees of sophistication. Either you can just blur it by a Gaussian kernel until the PSFs are roughly right, or you can try to make these kernels more sophisticated, or you can use many of the techniques that we heard yesterday in the different photometry talks, where this is really a critical part of the whole chain. Or you can do something in between, and that is to try to find a way where your images are convolved to a standardized point spread function, and then use standardized apertures that go with these point spread functions to have a very flexible control of this intrinsic aperture A cross P. And that's the approach that we're taking for our photometry in KiDS. So this is the technique that we're calling GAAP, Gaussian Aperture and PSF photometry. And it's really very useful if you're combining many bands with a spread of point spread functions, which is not too large, but is certainly large enough to worry about. So we standardize the point spread functions to Gaussians, and we use Gaussian apertures, which can be elliptical, to do all our photometry. And it's nice and flexible. You can optimize the apertures to be close to optimal for signal to noise. So you basically make them match the typical size of your source so that you don't end up measuring lots of noisy sky. And you end up with optimally, or almost optimally, signal to noise wise, and very much consistent, so PSF compensated aperture photometry. The benefit of this scheme is that if another band comes in later, you don't have to redo everything. You can simply add measurements to your SED. As I said, you can choose your aperture to have pretty much optimal signal to noise ratio for your colors. You're focusing on the central parts of galaxies, which tend to be more photo-Z friendly. They tend to be older populations, so they have bigger breaks. So that's a nice side effect for our photometric redshift measurements. And this is all completely independent of pixel grids, astrometry, camera, etc. This all happens in, if you like, an intrinsic sky coordinate space. So combining data from different cameras and so on is actually no big deal. It starts to break down if you have very large seeing ratios to bridge. So it's really only tailor-made for the kind of surveys that we're dealing with here. And it doesn't even pretend to try to measure total fluxes. This really is all about measuring consistent apertures to get good colors for these sources. Okay, so a little bit more detail. Here is the main formula again. This is how aperture photometry works. Intrinsic times this convolved aperture function. If A and P are now Gaussians, then of course the convolution is a Gaussian as well. And so this is nice because convolutions and deconvolutions become absolutely trivial. So what we do in practice is for every source, we choose what this aperture is going to look like. This P cross A, which I'll call W here, we set that to be a Gaussian of a certain size. Right, you can use an elliptical radius, and here's the size, and then the parameters of the ellipse tell you its shape. And this is going to be the same aperture for all the bands, right? The intrinsic aperture that you lay on your galaxy has to be independent of all your bands for all the bands that you're working on. And then for each band that you want to photometer, you take this intrinsic aperture, and then you compute what the post-seeing aperture function A would be by simply deconvolving the point spread function of that particular image from your intrinsic aperture. And then you do the aperture flux using this deconvolved aperture function. It's very simple. And so once again, these fluxes all correspond to the same pre-seeing aperture function on the galaxy, exactly what you want. And if you like, and what we do in KiDS is we do this for a range of aperture sizes, or a couple of apertures. And so this means you can actually do things like study color gradients, curves of growth, etc., if you like. And you can invent many more complicated things. You could have an aperture which is an annulus by differencing a larger Gaussian from a smaller Gaussian, for example. The other advantage is that this is, of course, all linear on the pixels. And so the error estimate is a simple propagation of the variance of the pixel data, or even the covariance of the pixel data. But of course, the point spread function is not really a Gaussian. This was a hypothetical example. And so our task is very simple. We have to make the PSF Gaussian. And this is absolutely the key step in this whole procedure. And to make a PSF Gaussian, you have to take whatever your observation gave you and find a suitable kernel to convolve your PSF and all the other pixels into Gaussian PSF. There's many ways you can do this. What we do in KiDS is we find all the stars in a coad, which is a square degree containing typically 1,000 stars that are bright enough for PSF measurements. You figure out what the seeing is and use that to set the target Gaussian point spread function size. Typically, we make the core of that Gaussian a little bit wider than the core of the PSF that we have on the images, because we're going to be moving flux from the tails into the core, and this is a nice compromise that stops you from really deconvolving aggressively and multiplying your noise. Too bad. So then, for every star, we ask the question, what would the Gaussianization kernel look like? Again, this is in principle an unconstrained problem, so you have to regularize somehow, and what we do is use a fairly stiff model based on shapelets. So we use the shapelet series. Shapelets are just Gaussians, circular Gaussians times Hermite polynomials. It's a nice orthogonal basis function. And we actually use a double shapelet model because these shapelet series cut off quite fast at large radii. And so we actually have a combination of two basis sets, one based on a wide Gaussian and one based on a narrow Gaussian. Where you have to drop some terms because otherwise the things get degenerate. So it's just, and again, another least squares problem that you have to solve for every single star that you want to use for this PSF element. So that gives you all over the image lots of little kernel models, and then we fit a smooth model through that to catch the way it varies across the image. And then that's your kernel. You convolve every pixel with the appropriate kernel. Because these are shapelets, this is actually, it's possible to make this very efficiently because they have very nice properties under Fourier transform. And then that gives you your PSF model, your PSF, your image with which has been convolved by a kernel such that the PSF is the same Gaussian all over the image. And now we've satisfied the requirements for what I described before, and we can do this photometry now with the Gaussian apertures. And it's exactly right, or it's as right as this convolution has performed well. And importantly, we propagate the noise covariances. It's basically the autocorrelation function of this kernel that we have. And you need to keep this to do your error analysis on the photometry of these PSF Gaussianized stacks. And again, this is fairly easy in shapelet space. So here's an example of how it works in practice. On the left here, you have two PSF stars from an image. This one's close to the middle where the image quality was very nice. In this image, one of the corners was not very good. The PSF was more elliptical than we like, or than we usually get in KiDS, in fact. So for each of these, you can construct one of these double shapelet kernels. You see it has both positive and negative parts. Pink is negative because you're bringing the wings in, but at the same time smoothing the core a little bit. And on the right here, you see what the resulting profiles look like. The blue is the original profile, where you see some scatter due to non-axis symmetry. And the red point is what it looks like after this kernel has been applied. The blue line is the target. So you do this, you end up with an image where this has been done all over the image, albeit with different kernels and therefore different noise properties in different parts of the image. So here's the residual. If you were to use just a single shapelet series, then you can do quite a good job in the center. So this is the difference between the delivered Gaussianized point spread function and the target Gaussian. Here is the target Gaussian divided by 100. So you see in the center, you really do an essentially perfect job. But if you use just a single shapelet series, you simply do not get out to large radii fast enough. And so you end up with residual flux in the wings. And that's what this double shapelet series is able to catch very nicely. Right. So here's an example in pixel space. This is just a small part of one of our KiDS images. You see the galaxy there with the elliptical isophote, with the elliptical aperture that we're going to use to photometer it later. This is the original stack. Now this is what happens when you Gaussianize it. You see that everything blurs a little bit, but the stars actually end up looking a bit sharper because you end up eating away the diffuse tail and putting it into a Gaussian kernel, whereas the galaxies get a little bit diffuse. So you nicely separate also visually the stars and the galaxies this way. You can repeat this whole exercise for lots of different apertures, different sizes, different shapes. And so what this plot here shows is that as a function of circular aperture radius, the signal to noise ratio is actually very flat. So of course it peaks at some sweet spot. When your aperture gets too large, you end up including too much sky. When it's too small, you miss too much galaxy. But the transition is actually nice and flat. So there is quite a bit of room to play to get essentially the optimal signal to noise ratio. And when you make the aperture elliptical to align it with the galaxy, of course, your signal to noise ratio improves a little bit more even. So that's what's shown here. All right, so this I would say, well, let me just re-emphasize a few of the points. So this process tracks the noise covariance because you keep the kernel of the Gaussianization. You model its spatial variation as well, so you can interpolate it in between the stars. And you can actually do this all analytically if you have an analytic model for the kernel, as we do with our double shaped series. So all you need is the weight image out of Sextractor, for example, and your shapelet kernel, and that tells you all you need to know about the noise properties in your PSF Gaussianized image. And the result of your Gaap photometry will be as good as the result of this step can be. So in KiDS, what we do is we make our normal stacks. We detect the sources and determine an estimate for the optimal aperture for the photometry. Then with PSF, we do this on our deepest image, which is the R bands on the coads. That's just to set the apertures. Then we PSF Gaussianize all our coads, the U, G, R, and I's. For the infrared data, there are very large gaps between the chips, so the coads actually have too big a PSF jump. So there we use the individual pole prints, the individual micro-dithered detector images. We PSF Gaussianize them all with a different PSF width, basically optimized to the seeing of each individual exposure. And then we go through this Gaap photometry procedure and we get the fluxes for all the bands. It's just a simple list-driven photometry, given the whole list of apertures that you started with. And you just build up the table and there's your photometry. So for the optical data, we actually use coads at the moment. We don't use the individual sub-exposures because the PSF jumps are very small and we found that it doesn't actually affect things. But as I said, for the infrared, we do have to do this on the individual prints. And standard, we use two different apertures, a large one and a small one, so that if you end up having to combine some image with a poor seeing other image, you have a larger aperture measurement available from the start. So it's all a very nice linear workflow, which is nice. So a quick word on stars. So I told you we don't care about total magnitudes at all for the galaxies. As it happens, for point sources, this Gaap flux actually is equal to the total flux. And that's because if you put an aperture on a delta function, if your aperture has a value of 1 at the center, then you're going to measure the total flux. Right? So here's our aperture in the intrinsic space. The intrinsic image of a star is delta function. The integral of the delta function times our aperture function is just 1. So it gives you the total flux. So for a star, no matter what aperture you use, elliptical, circular, large, small, you should always get the same flux out of this procedure, which is a nice consistency check. It also means we can very straightforwardly incorporate our photometric calibration into this whole scheme. For the stars, we are actually measuring total fluxes, which we can compare directly to standard star catalogs or whatever. It's also a nice star-galaxy separation tool, as it happens, because you can basically measure a curve of growth, and the curve of growth of this Gaap flux is completely flat. The total flux is always the total flux, no matter the aperture. So I'll quickly show you a couple of examples from each of these things. For the calibration, so these are all Gaap fluxes that we're getting from the stars in our field that we can then compare to some other catalog like Sloan or like Gaia, and we do a stellar locus regression. That means that all this information gets used properly. And so simply out of the catalog measurements, out of the single measurements, we have everything we need to do the kind of photometric calibration we need. So here's two different tiles. I have two different tiles here. And you see these have an offset, which we catch both in comparing to Gaia and in comparing to Sloan in the same way. So there's a whole other story about color terms and so on, which I'm not going to go into here, which once we start to use Gaia DR2 is going to give us a lot more information there. Star galaxy separation. This was actually a nice surprise how well this worked. So this is for one KiDS tile, 1 square degree, the ratio on the vertical axis, or the difference in the magnitudes corresponding to the Gaussian flux in a 0.7 arcsecond aperture and a 1 arcsecond aperture. And as I said, for stars, there should be no difference. So that magnitude difference is 0 here. You see this nice stellar sequence. And for galaxies, there's always more flux in the larger aperture than in the smaller aperture. So if you do some simple selection to try to pick out this sequence, and you then look at this in a color diagram, then these are the same objects, and you see indeed the things that morphologically look like stars by this technique. Also in terms of color, look like stars and not like the galaxies, which are a big blob of color space here. So this really works, and it works down to levels which are, it looks better than other ways to do star galaxy separation. So I think this is actually a nice way, and we will try to formalize this in terms of a chi-squared statistic or something. A nice way to get extra information on star galaxy separation, purely morphologically, and of course for every star you have 9 bands, so you can get a lot more information as well. So that was just an unexpected benefit. One slight issue which we have to think about, and we haven't fully worked through completely, apart from convincing ourselves that we don't have to worry about it just yet, is to do with centroid bias. So we have our detection image, and that detection image is also part of the images that we're using for the photometry. So of course you put your aperture on you peek up on your detection image. The detection image is slightly noisy, and so you'll actually have some uncertainty. And that uncertainty typically is of the order of the full width half max of your source divided by the signal to noise ratio for point sources or for the central parts of galaxies. And that will then also translate into a photometry error because you've put your aperture on, not quite on the central part of the galaxy. Now the colors in principle will be fine for all the bands apart from the one that you've done the detection in, where you have some bias because you tend to put things on top of a noise peak. And estimates of this bias are that it's something like 1 over the signal to noise ratio squared. So so for now, it's something we've convinced ourselves not to worry about, but it's on the to-do list to work this out and formalize this in a better way. All right, so in KiDS, all our photometry is based on GAAP. All the photo Z are based on these, the SEDs that we get out of this technique. As I said, we have no issue combining the small VST pixels with the much larger Vista pixels. We're able to combine data with a range of seeing between 0.5 and 1.3 arcseconds. It's quite fast. It's about a minute per square degree tile on not particularly fancy computers. And then the biases I discussed, actually, the reason we don't worry about them too much is that we're doing our photometric redshift calibration by comparing two data which have been measured in exactly the same way, same kind of data on spectroscopic samples. And so far, this really is doing the job for us. So we're very happy with this. On the possibly to-do list are a couple of further developments. One is to skip this whole Gaussianized PSF image altogether in the whole chain and write the whole thing just as a linear problem. In the end, you're just computing some linear combination of the pixel values of the source. And so you can write this whole thing, your intrinsic aperture deconvolved by the point spread function multiplied by the observed image. In principle, you can write this all directly as some very complicated aperture function and apply it directly to each source, which in some circumstances might be more convenient, in other circumstances it might not. Certainly, it gives a much simpler error estimate because you're simply computing an aperture function over the observed pixels, which are largely uncorrelated. But if you want to do many apertures, you have to calculate this thing every time, and it might no longer be efficient. And you might have other uses for this Gaussianized point spread function image. For example, for shape measurements, you can do something. And the second thing is how you do the point spread function Gaussianization in the first place. You can have an alternative approach, which doesn't involve shapelets, goes directly in pixel space. There are many different ways to do this. We've found that the shapelet model is nice because it's, on the one hand, sufficiently flexible to capture, to be able to make Gaussianized PSFs. On the other hand, it's quite stiff, so that you don't end up with lots of over-constrained coefficients that you then have to regularize in. But I wouldn't be surprised if there's really a better way. All right, I think that's the last slide, at least that's what my computer is telling me. So I'm happy to stop there and take questions.
Thank you, Konrad, for that, that excellent overview of galaxy photometry and a description of what you're doing in KiDS. Could we thank Konrad with a round of virtual applause on Slack, please? So we have quite a few questions queued up. The first one is from Jim Bosch. He's asked it on Slack, but has also asked that a moderator just repeat it because he has a squirmy baby on his lap. The question is, it wasn't obvious how this formalism breaks down when the seeing ratio is large. Could you elaborate?
So yes, so one aspect, if you're asking for a 1 arcsecond aperture, but you're seeing is 3 arcseconds, then this is not going to work because you're trying to deconvolve a small aperture by a large PSF. So your deconvolution simply breaks down. So if you're trying to convolve data over a large range of seeings, you've effectively got to make your aperture as large as the worst seeing that you're trying to incorporate. And then if that seeing range is really very large, then much of this is complete overkill. You could then simply convolving everything down to the very poor seeing of the worst seeing image is actually much more efficient. So it's not so much that it breaks down. I mean, it'll break down in the way we've coded it up, but it's not because the kernels will end up becoming very large and things like this. It's just not really very practical to do it this way if you have very large seeing differences. There are simpler ways to do it faster.
Okay, thank you. Next we have a set of questions from Robert Lupton.
Uh-oh. Sorry, Kuijken, you knew this was going to happen. Sorry, Konrad. You've chosen to Gaussianize the seeing and Gaussianize the aperture. Now, of course, you could have chosen to take a sharp-edged Petrosian aperture and map that directly to the seeing. And you mentioned some part of that in your last slide. Have you actually looked at using other choices of aperture, like Petrosian is an obvious one? You can still calculate the aperture exactly if you need to. Do you look at it?
I've played with a few things, but I was really focused on something where much of this can be done analytically because it's just so much simpler.
Okay, I wondered if that was the answer.
And when I saw how forgiving the signal to noise ratio as a function of aperture really is, I also lost motivation to try to do it in a more sophisticated way.
That's the classic plot for an aperture that gives you 1.5 sigma or something like that. So the next question, which you also partly mentioned, was you choose the aperture based on a single band. You use R band. So the noise propagation is much more complicated in the R band. It's not just a linear combination of the input variances. And so that must be true. You've already said you've got biases in that band. You've also got nasty variances. I was wondering how you actually calculate the axis ratios, however robustly, for really low signal to noise objects, signal to noise 5 sort of objects, where you've sacrificed a factor of 2 or 3 in signal to noise by working in a single band. Obviously, if you've got very different seeing in Viking, then the shape information isn't very good. So do you have any advice on extremely robust axis ratio estimation in the faint object limit?
So we are not using objects which are less than 10 sigma, because these are things which we're going to end up using in our shear catalog. So we really haven't focused on the very low. So this is why we use our deepest image for the source detection. Most of the other bands will be even lower signal to noise.
Okay. Somebody else, I think.
And so in practice, so one other thing, in practice, what we do is we simply take the source extractor elliptical RMS, AB, and angle, convolve that with the typical seeing in the other observations, and then that's our intrinsic aperture.
So that's basically a Gaussian fit, is it? I suspect it is. Most of the measurements in Bertin's stuff that don't say they're Gaussian fits are.
I think it's the RMS of everything inside the segmentation map, something like that.
Are you sure it doesn't use a weight? He often uses weights. Anyway, we can look that up.
I'm not sure about anything to do with extractor.
You have to read the source code. Let me see. I had one final question. Nah, that'll do. Let somebody else ask some questions.
We can come back to you, Robert, if we have time.
Yep. Thank you.
Next one up is Michael Wood-Vasey. Just a second, Michael, I'll unmute you.
Question withdrawn. It was the first item on possible future developments.
Okay, great, that's easy. Next up we have Gabor.
Okay, it's just a practical question that you said that you track the covariances between pixels. So what does it mean in practice? So of course in pixel space there are huge sparse matrices. So I guess there are more practical ways to do it. So how expensive it is in terms of tracking the covariance of the pixels?
No, we certainly don't have a covariance matrix between every pixel and every other pixel in the image. So it's really the covariance between neighboring pixels, and that is actually just the autocorrelation function of the convolution kernel. So it's a very compact thing, maybe 5 pixels by 5 pixels, or minus 5 to plus 5, something like that. So it's a very little matrix that you apply to every.
And how do you apply? So in shapelet space or Fourier space? In terms of calculation, for another convolution or deconvolution.
So turns out you can also do this analytically. It gets very messy, but because you can do all the integrals if you've modeled your kernel as a shapelet and your autocorrelation function is another shapelet, and that integrated by an elliptical Gaussian is something you can write down analytically. Though at some point the expressions get so complicated that I suspect the simple pixel sum is actually quicker.
Thanks.
Okay, so next up we have Eric Goizer.
Thanks. This is a very nice formalism. I just wanted to ask about the impact of galaxy sizes being a function of wavelength. So in this case, with the aperture size being fixed on the intrinsic image, which is an impressive thing to do, it still produces a different meaning of galaxy colors than if you were estimating the total fluxes in an efficient way. And I worry that that impacts the performance of photo-Z codes, especially template-based or empirical template-based codes, and imagining that you're getting the colors of the total galaxy. You talked a bit about spectroscopic calibration of photo-Zs. Is that how kids manage this issue?
So there's a number of different things here. So if a galaxy has a color gradient or a stellar population gradient, that doesn't actually introduce a bias here. It's just that you have to carefully interpret what you've actually measured. And what you've measured is the average color of a very well-defined set of stars distributed in a very well-defined way in your galaxy. So you are measuring a true color where every star in every flux measurement gets exactly the same weight, every star in your galaxy. As you correctly say, it's not the total flux because you're going to be missing more blue flux than red flux if the sources of the galaxy are blue. But you're still measuring a true spectrum of a true collection of stars, and so that should be perfectly legitimate for a photo-Z determination. So it's a real physical SED of a real physical collection of stars. Is that clear? Is that what you asked? You've probably been muted.
Well, I mean, that's part of it. I appreciate that. But if the empirical photo-Z templates were not made with what Robert's calling consistent colors, then you do have a disconnect.
I think they should, no, I think the colors are consistent. I don't know exactly what you mean by, I don't know exactly what talking about in terms of what Robert calls this. But these are real, I don't think there's a disconnect. It's not representative of the galaxy you're measuring as a whole, but it is representative of a particular true stellar population. Maybe we should try to take, well, this would have been a perfect coffee time conversation.
Okay, so let's thank Konrad again. And we will move on now to the next talk, which is, we have two speakers from the project, Jim Bosch and Dan Taranu, who are going to talk about project plans for galaxy photometry and model fitting.